Let's get started then with Chapter 4, Lesson 1. The title of the entire chapter is Congruence, a word that we introduced ourselves to just a little bit in last chapter. We go into quite a bit more detail with it in this chapter. As we read here right off the beginning of the chapter, two figures are said to be congruent, there's the word, if they have the same size and shape. That's a pretty good informal definition of congruent, same size and shape. Congruent triangles in particular appear in many important applications of geometry, engineering, architecture, and so on. Therefore, much of this chapter deals with the conditions needed to prove them so. In other words, we'll have some triangles and we'll, by proof, show that they have to be congruent. Along the way, and that's how we'll start today, we'll review coordinates in 2 dimensions, look at several types of triangles, important types of triangles, and then learn how congruence is the basic for geometric constructions. Meaning, we've done constructions already this year in the first 3 chapters, but we've never really defended our construction. We've kind of accepted it as true without proving it. We'll do that in this chapter. So today we start with coordinates and distance. And imagine yourself crawling across the desert and you see a sign that helps you locate yourself. Well, fine, you are there. We're missing something. What would be helpful? What would be more helpful than just to know where you were? Well, this would be helpful. I'd much rather see this. I'd like to see directions. And I'd like to see distances. If this segment right there is 1 kilometer, looks like we might be 1, 2, 3, maybe 4 kilometers from water, which if I'm in as bad shape as it looked, I'm probably not going to make it that far. So today, as we mentioned, we're looking at direction and distance. We're going to revisit algebra, coordinate graph system, find some distances on it. So segment AB, yeah, they look like rays, don't they? But we could find the distance from C to D and from A to B and from E to F. We could find those distances. It's a little tricky because they're slanted. It'd be easier to find distances like from there to there, as we did in class today with GSP. 1, 2, 3, 4, 5 units, or horizontally 1, 2, 3, 4 units. That'd be easy. How are we going to do it when they're slanted? Well, let's go back to even further than algebra. Go back to grade school where we used to have number lines. It was in 1 dimension. And as you're going from O to P, increasing, the ruler postulate comes into play. So there's our ruler. And what is the distance from O to P? Well, according to the ruler postulate, it's the positive number difference of their coordinates. So 2 minus 0 is 2. If we'd look at a number line without a ruler, we've got 4 points labeled there, A, B, O, and C. And we have 3 of them labeled with coordinates, -5, 0, and 5. How would you find the distance there? Well, there you see the coordinates. What would the coordinate for point A be? So we're starting at 0 and going back this way. So yes, it'd be -4. B would be -1, 2. We're hopping in a negative direction. C, now we're going in a positive direction. 1, 2, 3. So its coordinate would be 3. How about these distances? Well, the ruler postulate says positive number differences measure distances. So if we were to put the coordinates on here, maybe should have done that the first time through. So we have -4, we have -2, and we had 3. So now what are the distances up here? How far is it from A to B? Positive number differences. -4 plus a negative plus a positive 2. It's -4 minus 2. That gives you 2. And you can see that it's 1, 2 units. 2. BC would be 3 minus a -2. or 3 plus a positive 2, so we're looking at 5. And you can see that 1, 2, 3, 4, 5. And AC would be from negative 4 minus 3, which is the same as thinking negative 4 plus a negative 3, which is negative 7, but that can't be a distance, so we take the absolute value of that. So we'd end up with the distance from A to C is 7. So that was a one-dimensional coordinate system. Here now is a two-dimensional coming up, and we call that horizontal line the x-axis. And there's the origin where it's 0, and now we've added the y-axis. Do you remember what these Roman numerals are for? Those are the quadrants. There are 4 quadrants in a coordinate graph system. I've never heard of an explanation why it goes counterclockwise, 1, 2, 3, 4. That's always bothered me a little bit. There's probably a good mathematical reason. So we marked those off with a ruler, and we've got 4 points labeled with coordinates, 5s and negative 5s. So how do you locate points on a two-dimensional system? This should be review for you. We'd call this an ordered pair over here, x, y. The x-coordinate always first, and then there's a comma, and then the y-coordinate last. So here's how we do that. Always start at the origin, and then the x-coordinate. Well, we're going to the right, so it's a positive 3, and that is the first number in the coordinate pair. And then we do the y value. We went up to A, and now we just jog over to the left to see what measurement or what coordinate there is for that point, and that would be 4. So there's our ordered pair, 3, 4. Point B, labeling or finding that on the coordinate graph. Again, you start with the x value. In this case, we're going in a negative direction, so it's negative 5. And again, we're going up, which is a positive direction, so that in this case is a positive 2. So let's use this process on a two-dimensional coordinate system. So I just took that triangle off of that grid, and these are the ordered pairs, 1, 3, 5, 3, and 5, 6. So how far is it from A to B? Well, we're going to use the ruler postulate to get positive number differences. If we look at the y value, there isn't a difference, which makes sense. We're moving from A to B. The y, the up value, isn't changing at all. It's the x value that's changing. So we just take the positive number difference, 5 minus 1, and that's 4 units. Going from B to C, now we're going in a positive direction. We can't subtract the 5s. That makes no sense. So we're going to find the positive number difference here, 6 minus 3. And we end up then with distances like this. 5 minus 1 is 4. 6 minus 3 is 3. But how about AC? We run into some trouble when we try to do the same with AC, because now both coordinates have changed. So we can't just subtract 5 minus 1 and say the distance is 4, and say 6 minus 3, the distance is 3. What? That doesn't work at all, does it? But if we look at that picture and say, hey, that reminds me of the Pythagorean theorem. There's a right triangle. And we know 2 of the legs. We just calculated 2 of the legs there. We know that this one down here is 4. And we know that this one over here is 3. So we could use the Pythagorean theorem, couldn't we? We could say that 3 squared plus 4 squared equals this hypotenuse squared. And what I'd like to do right ahead of time is we would take the square root of that. So we're going to say that AC is equal to, it's going to look weird here on the picture, but I'm going to do it like this. The squares of the 2 legs added together. So that's what you see down here. You see AB is 1 leg up here, and BC is the other leg right here. We've squared them all, or both of them, like you do when you're working in the Pythagorean theorem. We took the sum of them, and then we took the square root to find the length of AC. So it looks like this when you use substitution. Substitution, we take the values that we had. Let me clear some of this out of here. So AB is from there to there is 5 minus 1, and BC is 6 minus 3 from up here. You just carry out the math, you subtract to simplify a little, then you carry out the squaring process, and we get the square root of 25, which then is 5. So we find out that the distance of AC is actually 5. Why don't you pause and give this one a shot? Try it yourself. Alright, so you're back. I hope you're doing this on your own. How far is it from A to B? Well, there's no change in the y, so it looks like it's 8 minus 3 would be 5. How far is it from B to C? Well, there's no change in the 8s, so the difference between 7 and 2 is also 5. So how far is it from A to C? Well, the distance formula would tell us what? The square root of 5 squared plus 5 squared, which is the square root of 25 plus 25 is 50. The square root of 50. That's an exact value, but we can simplify this, something that you need to get used to. Think about factors of 50. Well, 5 and 10, 2 and 25, those are probably really the only ones. If you can find some perfect squares in there, you can simplify this. And I can see that the square root of 50 would be the same as the square root of 25 times the square root of 2. Now we could simplify because we know the square root of 25 is 5. So 5 root 2. And that would be the distance from A to C. What we've done is we've used the Pythagorean theorem to develop something called the distance postulate, or distance formula. What if we just do it in general? See if this makes sense to you. The distance from A to B is taking x2 minus x1, because there's no change in the y. The distance from B to C is taking y2 minus y1. Again, there's no change in x. You'll notice here that if you take x2, then you have to take y2. Kind of important. And then from the distance of AC, we're thinking Pythagorean theorem in here. This time we didn't shortcut and get that square root in there right away. So we would say AC now is the square root of that. You can square both of these, or take the square root of both sides. And that's how we end up with that next step. And then substitute the values from the diagram over here. These guys, substitute those in. AB was x2, right up here we've got it. x2 minus x1 was AB. BC is y2 minus y1. That goes down here. And so here is the distance formula. This is something you're going to have to be comfortable with. Memorize that so you're able to use it. The distance between 2 points, P1 and P2, with these coordinates, x, y, x1 and y1, because it goes with point 1. P2 has coordinates x2 and y2, because that's point number 2, is this. So you find the difference between the two coordinates. It's a ruler postulate idea. Square it. The difference between these two coordinates, that's the other leg, and we square it. And then take the square root, and that will give you the distance between points P1 and P2. So here A and B, I've gotten the coordinates here, 4, 1, and 6, 6. So how long is AB? So maybe you can even do this in your head. So we take 6 minus 1 is 5. Square that is 25. 6 minus 4 is 2. Square that is 4. So we're looking at 25 plus 4. So here you see it now. 2 squared and 5 squared. 4 plus 25, that's the square root of 29. Now I'm looking for factors of 29, but that is a prime number. The only factors are 1 and 29. So we say then that this is the answer. That's the difference. This is the exact answer. If you punch that into your calculator, you're going to get some other number, which is going to be an approximation. So the distance formula that you're working with, you don't really need it for a vertical line. That's pretty easy, but would it work? Let's take a look. I've put the coordinates there. So let's punch out there the distance formula, and you see what happens right away. We've got the length, the change in x. It's 2 minus 2. It doesn't change. So this turns into a 0 right here. 0 squared is 0. So it basically just disappears, doesn't it? And you're left with just this part, 6 minus 1, which was the change in the y value. 6 minus 1 is 5. So you walk that down and you get 5 units, which you can count. 1, 2, 3, 4, 5. So the distance formula would work for that. It's just a lot of extra work. It will also work for a horizontal line, as you can see here. This is kind of nice to look at because I don't like to subtract numbers. I like to add the opposite. So here we add coordinate -6 and -2, and we're finding the difference. I like to think of it as -6 plus 2, which is -4, squared is 16. What happens to the y values? They don't change. They stay at -4. -4 plus a +4, add the opposite, is 0. So we're down to the root of 16, which is 4. So the distance formula, it works for horizontal lines, vertical lines, and diagonal lines. Chapter 4, Lesson 1, there's some problems working with that. Maybe you used one of these pin boards, or geoboards, I think is another name for them. So they've got a geoboard here, and they formed some figures. A triangle was green and a red square. And just some questions. They've superimposed the coordinate graph, the x-axis and the y-axis here. So use that to answer those questions. There are a few more questions here about that. In the dictionary, the word grid is a pattern of horizontal and vertical lines, forming squares of uniform size on a map, chart, or aerial photograph, or a geoboard like that. That's a grid, used for referencing and locating points. So now a couple of questions about that. Which axis would be the horizontal and which one the vertical? How many numbers do you need to locate a point on a grid? And if you were under fire, if people are actually shooting at you, trying to kill you, and you had to look at a map for your survival, you'd want to be able to read it pretty quickly without any, oh, which is the x-axis, which is the y-axis, how am I going to get in the right spot? Well, they teach soldiers this so they can deal with it under pressure. They say, read right up. So I got my map, I just have to read right up. Well, how does that make sense? See if you can figure out why that makes sense. And then what are the coordinates of point A? Another definition would be a football field. Is that a good grid? They call it the gridiron, actually. Is that a good model of a grid? So there you see a football field. Pausing and then move on. So here's another coordinate grid system. Coordinates 1, 2, 3, and 4. Quadrants, I should say. And then they've got coordinates labeled positive 10, 20, 30, and negative 10, 20, 30. And this big yellow area is the area occupied by bats. The rest of the labels on here are birds. And they're classifying them by two characteristics of their wings, a high aspect ratio and a low aspect ratio down here. Broad wings, thin wings. And then we've got high loading with small wings and low loading with large wings. So with this coordinate graph system, you're to answer some questions here. So back and forth looking at that picture. And then this one gives trouble sometimes. What are the approximate coordinates of the 2 points in which the bats region intersects the x-axis? So here are the bats. Remember which one's the x-axis. Here it is. And what are they asking? They're asking for the approximate coordinates, both the x and the y values. So Isaac Newton had a book, 1704, called Optics. He knows how to spell. That was just the way they did it back then. They've got all 4 quadrants shown there. And there are 3 questions trying to see if you can cipher that out. It's got a bunch of other lines and such in there. Geometry is involved even in navigation and geography and currents. Here we've got currents going through between, where is that? Chesapeake Bay, it says, Chesapeake Bay. Directions of the currents. And here they've transferred them into a coordinate graph. Same one we used in the lesson today. And the first question, what seems to be true about those currents on that graph? And then some questions. Find coordinates and calculate their length. There are 3 of them here, so there's a few points here. You need to use the distance formula on all 3 of these. Looks like I'm giving you a little help on the first one. So 6 is the x value here, and 4 is the x value here. 0, 1, 2, 3, 4. And the x value of b is 6, so 6 minus 4 squared. And then 6 minus 1 squared, the y values. We've got 6 minus 1 squared. So we've got 4 plus 25, or root of 29, using those 2 points. So you've got 2 others to do, CD and EF. And then they were asking on 30 whether what you thought on 26 was true. A floor plan of a Japanese home. So here's the floor plan right here. Here's the post pattern on the left, so you put those posts in first and then you'd construct the floor and the walls after the fact. And they're on the same grid. This whole thing here is a grid. It's just they've got 2 separate drawings of it. Kind of picture the origin down here, 0, 0. And it tells us that in the directions. Lower left, and they're 1 unit apart. So now, using this as a grid, answer questions here about the different points. And then get you to think about it. How are the coordinates of each point on the floor plan related to the coordinates of the corresponding parts in the post pattern? So how are these points, A2 and B2, related to A1 and B1? Where would the floor plan appear on the grid if the x-coordinates of its points, the x-coordinates, matched those of the post pattern, but the y-coordinates were 10 units larger? What would happen? Where would this grid, where would this floor plan be? Would it be down here? Would it be over there? Would it be over there? Would it be right there? Would it be right on top of it? What would it look like? Something you use all the time, computer screens. I don't know if you're aware of it or not, but we measure computer screens by pixels. How many picture elements, that's what that stands for, are there on a screen? You maybe know some high definition, 1024 by 768 gives you 1024 in one direction and 768 in another, and they get even higher, much higher, on newer monitors with clear resolution. So the coordinates are usually given in pixels. Suppose the coordinates of two corners of a window on the screen are shown below. So this is point A down here is 100, 200. Remember, this is the X, and that's the Y. And up here we have 900 and 800. So I think it's important to think about this. I'm showing you approximately where the X-axis might be and the Y-axis. So down here is 0, 0. So they're saying point A right there would be 100 this way and 200 up that way. Whereas point C over here would be 900 on the X-axis and 800 up on the Y-axis. So with that in mind, answer the questions here and figure out the distance. Suppose that you use the computer mouse to click on one of the three icons. Which one would it be if you clicked on 410 by 670? Think about that one. That's a good challenge. They're going to have you get these other two here and then try to figure out where would 410 and 670 be. Using the distance formula in general, write the formula for distance between those 2 points, then use it to find the distance between opposite corners. Leave it in radical form. That's absolute, exact form. Don't use your calculator to get the square root of anything. And then some questions. Would it be correct to say that the distance formula for one dimension is this? So like on our lesson and in GSP, we went from, say, a point here over to a point there. Would this give you the distance? If so, use it to find the distance between those 2 points. Now we've got something in 3 dimensions, and they're giving you the formula and asking you to use it and answer a question about it. And this is going to mess with your mind a little bit. Distance formula for 4 dimensions. They want you to write the equation. Look back at the previous 2 examples. I think you'll get it. And then use it to find the distance in 4 dimensions between the opposite corners of this hypercube. That's what you call it in 4 dimensions. There up to there. How far would that be? Giving these pairs of points. We've got 2 triangles here, a blue one and a red one. And they've given you the coordinates. And they want you to find the lengths of the sides. So there are 3 equations that have to happen on this one and 3 on this one. So stay at it. It's going to take a little bit of effort there to find those. And then finally a set 3, a circle challenge. A through F appear to be on the circle here. But they tell us 2 of them aren't. One of them is inside, one's outside. And they want you to try to figure out which are which and explain how you did that. So this is Chapter 4, Lesson 1. Hope you get at it in time to ask some questions. That would be great, and it would be to your advantage to do.